Mic is okay? Yeah, okay. Okay. Thank you. Thanks for having me. Good. Thanks for having me. Yeah, so it's nice to be giving this talk. So when I was asked to give this talk, I was wondering what should I speak on? What sort of topic I can talk about? And I decided I will actually talk about something, a very basic paradigm in computer science, in theoretical computer science, called the divide and conquer paradigm. If any of you have taken an algorithms course or will take an algorithm course sometime in the near future, you will see this paradigm of divide and conquer. And it's a common paradigm. We encounter it. I also encountered it eons and eons ago when I did my undergrad in computer science. I saw divide and conquer. And I thought it was just a paradigm which occasionally we use this one. And I completely forgot. I didn't use it much later on in this one. So I would, of course, I've used it to solve problems in my undergraduate classes and later on, but never actually as a tool during my research work or anything subsequently. Till recently, Rohan Goyal, who was an undergraduate student over here at CMI, visited me 2 summers ago for a summer project back in TIFR. And we were talking about some problem in coding theory and some question which I was interested in coding theory, and I was trying to focus on the problem, trying to get, and then we came to a slightly smaller version of the problem, a sub-problem in the bigger problem, and we realized we did not know how to solve it. And finally, what we later realized is divide and conquer came to our rescue. So what I thought I will do in this sort of story is I'll first give a brief introduction to the problem we cared about, then we'll take a long detour into divide and conquer, and if time permits, we'll come back to the problem that Rohan and we worked on later on. By the way, feel free to stop and ask me questions at any point of time. Feel free to interrupt me any point. So this work is based on this work that Rohan, Mrinal Kumar, who's my colleague at TIFR, and Ashutosh Shankar, who's a graduate student of mine. Ashutosh was also an undergraduate student from CMI who then is currently doing his PhD with me at TIFR. There's a work of us which appeared, with a very recent work of us which appeared last year. So what's the problem? So we wanted to, while solving, there was some problem in coding theory that we cared about. That problem is not of interest for this particular talk. We wanted to solve some differential equations. Differential equations of, many of you, even if you don't know what differential equations are, equations of this type. So it's just something like you're given x plus, say 1 plus x plus dy by dx into x cube plus d square y by dx square into 5x plus 2 equals 0. So, and I want to find all polynomial solutions y as some function of polynomials to the above differential equation. So it's some such problem. So you're given, so why do we care about such differential equation? They appear a lot in mathematics, but from computer science, from the computer science point of view, these differential equations do appear when you're working with error correcting codes, when you're doing noisy interpolation, Hermite interpolation, and all. You'll get these sort of. Is the mic okay? Okay. So we'll get these. This is not of interest to us. So just to be a little more formal, I'm going to put this problem, state this problem more formally. So we're going to be given such an equation. You're going to be given some equation of this form. And you want to find all polynomials p that's in the, so this polynomial has several variables. It has one variable which is x, and then there are these other variables which are y0, y1, y2, ym minus 1. And this equation polynomial, if you look at this equation, it's linear in all those other variables, y0, y1. With x, it could be an arbitrary polynomial. For example, in this setting, this will be like 1 plus the corresponding case over here will be 1 plus x, y1 into x cube plus y2 into 5x plus 2. That's the polynomial q of x, y0, y1, y2. That's the polynomial. You're given such a polynomial. And I want to find all polynomials p of x such that when I plug, instead of y0 p of x, instead of y1 I plug the first derivative of p of x, instead of y2 I plug the second derivative, and instead of ym minus 1 I plug the m minus first derivative, this equation vanishes. That's what I want. I want to find a solution to this differential equation. And I want to solve it. I'm only interested, so when you solve differential equation, if you have, any of you have seen differential equations could appear and also they could be not necessarily polynomial solutions, they could be sort of exponential solutions, trigonometric solutions and all. But for the purpose of this talk, I'm just going to focus on trying to find those solutions which are in the form of polynomials, and polynomials of degree at most d. That's the focus. So why do we care? First thing, let's see. Suppose you want to solve the system. Is this system solvable? Now, because we care only about polynomial system, one thing to notice about it is, this is just if you write down this polynomial in terms of its variables. More precisely, you can write p of x as p0 plus p1x plus p2x square and so on up to pdd x to the d. Solving this polynomial means actually finding out the coefficients p0, p1 and up to pd. You can just now plug this set of coefficients into this system, and then you will get a huge equation. You will get several equations in p0, p1 and pd, and notice that they are all linear equations if you'll actually look at it down. So you can write one big matrix. It's a linear system. You can write a matrix. You can just write a system of equations and P will be a solution to this. More precisely, all I'm saying is this system can be solved just using Gaussian elimination. So this is not a hard problem. It can be solved. It's a linear system in P0, P1, P2, PD, and you can solve this. But if you recall, if you're going to solve a linear system of equations, typically it takes cubic time or quadratic. Typically it takes cubic time or at least quadratic time. Any typical solution for solving. By the way, if you don't follow these, stop me or we'll come down to more basic problems in a slide or two. Just typically solving this would take d square or d cube time if the underlying polynomial is of degree d. That's a linear system. But for some of the applications that we care about, I want not just d square or d cube time. I'm not sufficient happy with the polynomial time algorithm. We really want a super fast algorithm. An algorithm that is nearly linear. An algorithm that takes only order d time. So once again, this is the problem. What we want, what I want is a nearly linear time algorithm. Basically, I want an algorithm, so it will take linear time even to write down the coefficients, P0, P1, PD. I want the algorithm to take not significantly more amount of time. And this is what we wanted while solving this other paper. We wanted to know if you can solve this problem more efficiently. And in fact, what we did we eventually gave a nearly linear time. In that paper which I mentioned, we gave a nearly linear time algorithm. We gave an algorithm which was d polylog d algorithm. And firstly, notice a couple of things. The first thing the most important thing for us in this talk is this algorithm was obtained using a divide and conquer paradigm, and that's what's going to be the focus of the entire talk. And as I mentioned before, notice this thing is taking very little, it's taking just a little more time than to write down the solution. So it's hardly any this one. And came about this. So what we'll do in the rest talk is I'm going to introduce the divide and conquer paradigm. In fact, I'm going to introduce it to two problems, merge sort and polynomial division. One of them, some of you might have seen it. One is a textbook example. Other is a slightly non-standard example. We'll see both of those. And if time permits, we'll come back and see how those methods actually solve this problem. Yes. Polylog, so this is how much running time is, polylog is logarithmic. It takes, the running time is d into say log d to some cube. That's all I mean. So some fixed constant, either it's 2 or 3 or 4 or this one. The problem, finally, I think our solution will be d into log d to the power cube. Okay. So this was just a brief intro. We used this to solve divide and conquer. So I'm going to now take a long detour to understand what divide and conquer is, why does it help you, why does it give you such fast algorithms? Why does it give you such fast algorithms as d polylog d? Okay. So what's the divide and conquer paradigm? The divide and conquer paradigm is, as the name suggests, this paradigm in computer science is, suppose you're asked to solve some problem of a particular size. You ask if the problem can be broken down into two or more smaller parts of the same type. If you can break one problem into smaller parts, solve those problems, solve those individual parts. This could be 2 parts, 3 parts, 4 parts, how many ever parts. And then, so you solve the 2 parts separately. Notice that this is not a solution to this problem. And then you try to combine the solutions. A divide and conquer paradigm is this general paradigm. It has sort of 3 steps. The first step is the divide step. Somehow you take your given problem, break it up into parts, into 2 parts or so. So split the problem into smaller subproblems. Then you do this conquer step, which is solve each of the subproblems recursively, separately. And then you sort of combine the problems. You merge the solution to get the solution to the original problem. It's this recursive thing. And it has several advantages. Well, code is it sort of breaks the problem by recursively breaking into smaller subproblems. It simplifies complex problems and improves efficiency. And there are some standard textbook examples like merge sort, quick sort, division. So let's actually get our hands dirty in the next 10 minutes or so and see some of these examples and see what divide and conquer gives for us. So our textbook example is going to be merge sort. I don't know how many of you have seen merge sort as an algorithmic paradigm. Cool. Most of you have seen. So this will be very familiar. So at least more than half has seen. So this will be familiar territory. So what I want to do, I'm going to give 2 examples. One is merge sort, which is an example of divide and conquer. What about polynomial division? All of us, of course, know how to do division. But how many of you have seen division using divide and conquer? Good. So far lesser. So hopefully there will be something new over there. For example, for me, I knew merge sort. I did not know polynomial division till about 2.5 years ago. And this project was what led me to this. So let's see what merge sort is. What is the sorting problem? You're given an array of n elements, which say n integers, say, and you want to sort these elements. That's the basic problem. You're given n numbers and sort it. And there are you would have seen several ways to do this. Possibly some of you have seen quick sort and all. How does the way of merge sort go? You split this is a very natural way to do it. Merge sort is you split the array into 2 parts. The first half and the second half. 2 more or less equal halves. If the array is of n even number of elements, you can split it into exactly 2 halves, 2 equal halves. Otherwise, one more than the other. Now, recursively use the same routine to sort the problem on both the halves. And then you have now 2 sorted lists. You just need to combine it into one single list. You can run a linear time algorithm to combine this. That's a very you can think of how this goes. So let's actually see one example. So suppose you're given this array of 7 elements, 38, 27, 43, 3, 9, 82, and 10. How would you go about doing this? The algorithm in the first step will split the array into 2 halves. The first half, which is now 4 elements, 38, 27, 43, and 3. And the second half, which is 9, 82, and 10. And then it recursively solves the 2 halves. So the first half, when you sort it, you get 3, 27, 38, 43. The second half, when you sort it, you get 9, 10, 82. So now you have 2 sorted half problems. you sort of merge them. You know the first element should be either 3 or 9. Find out which is the smaller, you put it first. Then, so you put 3. Then the next element should be either 27 or 9. It's 9, you put 9. The next element is either 27 or 10. It's 10, so you put 10. So it should be then 27 or 82. So it's 27, 38 or 82, put 38, 43 or 82, 43 and 82. So you just go through the two lists from left to right, and while doing it, you can just put them in, and that is the sorted problem. So that's great. So what's actually happening here, if you unravel the recursion, this is what is happening. You had this original 7 elements. We broke it up into 2 parts. Now recursively, that is further broken up into 2 parts. The first half, the second half. This is broken up into 2 parts. One. Once again, that's broken up into 2 parts, 2 parts, 2 parts. One. And once you are with single element arrays, there's nothing to sort it. And now you merge these two. When you merge these two, that's the sorted part. When you merge these, combine these two, that's the part. 3 and 43 are 2 sorted arrays. You're combining them, that's 343. When you 9 and 82, when you combine them, you're going to get the same thought, 10. Then you combine these two, combines it. That's what, it's a complete unraveling of the entire merge sort algorithm that we have said. I'm unopening the recursion completely over here. So this is the algorithm that runs. Let's try to understand what's the analysis of this algorithm. Let's see how much time does it take. So let Tn be the amount of time required to, we're going to assume it takes a unit amount of time to compare 2 elements. And then given that, we're going to ask how much time does it take. So let Tn denote the running time to sort an array of n elements. So what have we shown? The divide step will take order n, because you just have to go through it and split it into half. That takes about linear time. The divide step is order n. The conquer step is 2 subproblems, each of which involve things of size n by 2. So it's 2 times Tn by 2. That's what the conquer step does. Sorry, this is a typo. This is a combined step. The combined step, when you merge them together, it takes linear time. We saw the merging that happened, and that takes order n. So what have we shown? We have shown that Tn, the amount of time for n things, is 2 times Tn by 2 plus 1 order n over here plus another order n. That's the recursion. So we have sort of a merge sort analysis is the recursion which we have is Tn is equal to or less than or equal to 2 times Tn by 2 plus some order n. That's the amount of time we take. And now we try to understand how much time this recursion takes. Amazingly, this one, if you solve this recursion, you will get that n log n is the answer to this recursion. And that's why merge sort, you take only n log n time to sort n numbers. The amazing power of divide and conquer is basically the heart of what we saw previously is this recurrence relation. It is showing that you are breaking up a problem Tn, a problem on n parts, into 2 problems of n by 2, this one, and then in the divide and combine steps, you are at most spending some order n time. And that's why it's this magical recurrence which gives you the answer of Tn order n log n. Okay? Any questions on merge sort? There's something all of you possibly have seen, and I'm just boring you with the details over here. But I just wanted to tell you it is this, it's because we get this recurrence relationship when we solve merge sort is why we get order n log n. Okay? So much so far for merge sort. What we'll now do is we'll go to another problem, polynomial division, and ask if we can do the same, if we can repeat whatever we have seen so far to do for polynomial division. Okay? So what's polynomial division? Polynomial division is this problem. You're given, say, I give you 2 polynomials, say ax and bx, and they are of, let's assume they are of exact degrees capital D and capital D minus small d. These are the degrees of the 2 polynomials. Let's even, for simplicity, assume but both the polynomials are monic. That is, their leading coefficient, that's it, the x power capital D degree in ax is 1, and the x power capital D minus d degree in bx is 1. Let's assume that. What I want to find out is I want to find the unique degree d polynomial p of x such that when I divide a by b, I get p of x. There exists one such polynomial, or possibly there does not exist such a polynomial. What I want to do is find such a polynomial. Notice this is something we can do. It's exactly, you can imitate what we learn long division, the long division which we learned in in the second grade or third grade. We can do exactly the same thing for polynomial. You can do it and you can find out if b divides a, and you can find out the quotient which is p of x. This is something we all have learned to do. This is long division. Bad with this. Yeah, long division. But there's a reason why it's called long division. It takes a fair amount of time. If you notice it, long division, if you actually are very careful how much time long division takes, it takes quadratic amount of time. It will take you order d, capital D square, the larger of the 2 degrees. That's the amount of time it will take. Now you can't afford to spend, each time you do division of degree d polynomials, you can't afford to spend quadratic time. In fact, when you run a program, if you write a code to solve division, you cannot use the algorithm that we do it to learn in middle school about division. That algorithm is too expensive. You'll have to run faster algorithms because a quadratic algorithm is not something that you can run in practice. It's too slow for as basic a problem as polynomial division. So what we'll see is actually there is a divide and conquer approach to solve it in d polylog d time. So that's what we are going to see in the next 10 minutes or so. We'll see how polynomial division can be solved using divide and conquer in order d polylog d time. And the reason I took an example of polynomial division is, in merge sort it was clear. We had n elements. You wanted to sort it. It was easy. Break it up into half. You can sort the first half, you sort the second half and combine it. It naturally led itself to a divide and conquer algorithm. Now polynomial division, where does the breaking up into 2 parts come? So I've given this problem. I would like to break this problem into 2 smaller problems, also which look like polynomial division. Say if I can solve them, I want to glue them together to solve the original problem. On the face of it, this is not a problem which looks as if it can be broken up into 2 parts. At least it's not obvious at all that this can be broken up into 2 parts. So what we'll see in the next, this one, we'll actually see how to break it up into 2 problems of smaller this one. And then once you do that, it will be immediately amenable to the whole divide and conquer paradigm. And we'll once again get we will come up with such a recurrence relationship, which we had a similar recurrence relationship. And once we have such a recurrence relationship, we will know that this problem also has a nearly linear running time. Questions so far? Yeah. So what's this one? By the way, what I'm talking about for the divide and conquer algorithm for division is actually works of Sievking, Kung, Strassen from the 1970s. It's a beautiful application of FFT, the Newton iteration and divide and conquer. This is what I'm going to talk about in the next 10 minutes or so is work from the 70s, which is what we use today in practice if you want to do polynomial division. Yeah, when you run a program for doing polynomial division, it's these works that are used to do it. Okay. What's polynomial division? So once again, let's rephrase the problem. Okay. So we're going to do polynomial division by a divide and conquer. So once again, so far, what do we want to do? The way I stated the problem, there was no mod x bar d. We just wanted to find, given a and b, we wanted to find a p such that ax minus bx is identically equal to 0. What we'll try to do is, instead of solving it as a full polynomial identity, let's solve it only up to, say, a particular degree d. So here I'm going to, strictly speaking, this should be d plus 1. I'm going to fudge things. I'm going to write x bar d instead of x bar d plus 1. So suppose we solve it up to x power d plus 1, mod x bar d plus 1, then we can then notice that because all the degrees here are at most capital D, if I solve it up to x bar d plus 1, then a solution to this modular equation is also a solution to the original problem I had before. So this is actually d plus 1, but ignore it. D or d plus 1 is not going to make a difference. So what I will do is, instead of solving the problem original problem, I'll solve this modular problem. I just want to find a p so that ax minus px bx is congruent to 0 mod x power d. And now once I rewrite it this way, notice once I write mod x power d, now we are going to sort of do a divide and conquer on this coefficient d over here. That is, we'll try to make this smaller and smaller and try to solve the problem. And we'll show that you can solve. For example, if I had written mod x, if d was 0, if d was 1, what was this equation be? This would have just been, if I am writing ax minus px into bx congruent to 0 mod x. Then notice all the high degree terms will vanish in this equation. This equation will just become a0, the constant term of a0, the constant term of p0, and the constant term of p, which is p0, the constant term of b, which is b0, is equal to 0. This equation just collapses. This top thing is the same as this one. This you can easily find out because then p0 is just going to be a0 divided by b0. It is one field element by another. So it's this integer, this rational number divided by this rational number. So then when x is equal to 1, when capital D equals 1, it's easy to solve. So we're sort of trying to do this sort of an approach. We will now try to see, can I solve p? I want to find a degree d polynomial p of x. Let me write it as the low degree part of p and the high degree part of p. I'm splitting p as two parts. This is the low degree part, u of x, and v of x is the high degree part. So every term here is pre-multiplied by x power d by 2. Once I write it this way, this equation, let me redo this on the board, then going over the calculations there. So we had this, I want to solve this polynomial, ax minus px into bx is congruent to 0 mod x power d. And we'll set p of x to be equal to the low degree part and x power d by 2 into v of x, and this together is the high degree part. So if I do this, then the above equation is just a of x minus u of x plus x power d by 2 v of x into b of x is 0 mod x power d. So let's rewrite this a little bit. So this is a of x minus u of x into b of x plus x power d by 2 I just rewritten the above equation over here. Now notice, the thing to notice out here is, sorry, this is capital D. In this equation, this part does not contribute any low degree terms. This part is fully high degree. Any low degree contribution to this equation should only come from this part. So in other words, if this has to be 0 mod x power d, it must be the case that a of x minus u of x, b of x should be congruent to 0 mod x power d by 2. Because this thing has 0 coefficients, all the coefficients less than x power d are all 0. This cannot contribute anything in the low order part. Therefore, this part should not have, if it has any contribution to the low order part, then the whole equation would have a contribution to the low order part. Therefore, this So this equation is the same as this. In fact, this is if and only if. This certainly implies this. But it's not sufficient. This will say the low order part is 0. But then you also want then the high order part to be 0. So what I want to say is, so now you solve this. Now notice when I'm solving this, I can drop out, this equation is mod x power d by 2. I can just drop out all the coefficients which are larger than x power d by 2 over here. I can work only with very small, much things smaller than x power d by 2, and you can solve, suppose we can solve this. How do I now find, so this will lay my hands on u of x. How do I lay my hands on v of x? Notice that this is an implication. For it to make it a if and only if, this should be equal to c of x minus x power d by 2 v of x b of x. Let me write it as, yeah, b of x, v of x should be 0 mod x power d, where c of x is in fact exactly what I got from above. That is all the, so that should be 0. This is what exactly written here. This should be both 0. Now this problem, this part looks exactly like how I want. This is exactly the same equation as above, but with a smaller d by 2. So it looks like I've broken the big problem into one problem of smaller degree. But the other problem does not seem to be of smaller degree. But let's just stare at it. Notice this c of x is what this guy is. Now if he had got the right u, this c of x is a multiple of x power d by 2. If I had got the right u, this c of x, because c of x is exactly this equation, is this part, the left hand side of this equation, it will be, it's going to be 0. So in other words, c of x will be actually, this c of x will be some x power d by 2 into c tilde of x. If I had calculated the u correctly. Therefore, this equation that I have here becomes so this equation which I had here, which was that c of x minus x power d by 2 b of x v of x is congruent to 0 mod x power d. This equation becomes x power d by 2 c tilde of x minus x power d by 2 b of x v of x congruent to 0 mod x power d. Now, if this has to be 0, I can just cancel an x power d by 2 from the whole equation. And what we would get is, so this is the same as this, and this is the same as c tilde of x minus b of x into v of x is congruent to 0 mod x power d by 2. Yes. We require multiplication to be fast. So because why do I need multiplication? Exactly, what's your name? David. So where do I need multiplication? I'm using multiplication for in computing c of x, I need to multiply u of x and b of x. And we want to know whether multiplication can be done. We need multiplication to be done fast over here. If this multiplication took quadratic time, if you had done multiplication the way we do in middle school, that is you do long multiplication, that will take quadratic time. Once again, polynomial multiplication, some of you might have seen, is you use this Fourier transform, fast Fourier transforms to solve it. And that actually gives you the polylog d times, d log d time in fact. You can solve this. So what I will use here, I'll come to that. This step, I will actually use a fast multiplication. It's also an application of Fourier transform, but It's usually mentioned in a different way. You go to this, if people haven't seen polynomial multiplication, you go from a polynomial can be represented both in the, so how do you do multiplication very fast? The multiplication is done very fast in the following sense. If polynomials can be represented in two different ways. One, you can represent it as a list of coefficients. You can also represent it as a list of evaluations on, suppose you have a degree d polynomial. If you give me its evaluation at d plus 1 places, that is enough to get the polynomial. So you can give the polynomial either in the evaluation as a list of evaluations or a list of coefficients. Now, notice when you look at it this way, these are the same thing. They both represent the same polynomial. But if you ask with respect to algorithmic efficiency, one is much easier. So if you give me in the coefficient base, if you give me a polynomial in the coefficient, it's not clear how to do multiplication easily. But if you give me in the evaluation basis, how do you multiply? You just take point by point. If you have the evaluation at a point and an evaluation of one polynomial at one point, another polynomial at another point, just multiply the two evaluations, you get the evaluation of the product at that point. So you can get, so if you had the evaluation of, if you want to find the product of two polynomials A and B, you take evaluation of A on 2D points, B on 2D points, get the two evaluations, and then just multiply them point by point, you multiply the evaluations and you get the evaluation of the product polynomial on all the 2D points. That is very fast. But then the problem is, how do you go from the coefficient basis to the evaluation basis? And that's what the fast Fourier transform does. It gives you a way for going from the coefficient basis to the evaluation basis in d log d time. It in fact does, you need to do both ways. The first you go from the coefficient basis, you go to the evaluation basis, that's this one, then you do the calculate products and then come back, you have the product polynomial in the evaluation basis, you come back to the coefficient basis, that's the inverse fast Fourier transform. Just one question, you had a question. Okay, yeah, David. Huh? Division can't we use the same? Huh? Divided and do the field. I could do the exact same thing. You could do, huh? You could do the DNA thing. Yeah, you could do a similar thing. The reason I'm going to do it is, the reason I'm going to do this way is this is what is going to help me for the other approach. Okay. By the way, both the approaches which I'm stating, actually, if you stare at it a little closely, the approach which I mentioned and the approach you are talking about are actually the same approach. They are the same approach. It will take me, I won't be able to tell it in this lecture, but I can talk to you of this one and tell the approach which you had and the approach I have is exactly the same approach. They have this one. It is splitting evaluation of polynomial. So there, what are we doing? We're taking the evaluation of polynomial on d places. We're going to break it up into d by 2, which is the same d by 2 and d by 2 that's going on over here. This is a more general setup of that problem. Anybody else had a question? And I'm stating it in this reason. For a particular reason, it will lend itself to the other problem. Huh? No. At this time, it's going to be difficult for me to tell why it is same. Both approaches are, this approach which I'm giving subsumes his approach. It's sort of essentially, it is a more general version of whatever he is stating. Yeah. If it doesn't divide, then it's a problem. Yeah. If it doesn't divide, then it's a problem. Yeah. So, in general, what Chandra is stating is, when it's exact division, for the original problem, for the exact division, this works. But suppose you're just interested in the modular division problem, then this one necessarily does not work. Whereas what I said will go through. Okay. So now what have we done? We have satisfied, we wanted to solve a P, we have broken it up into two equations. And both are exactly of the same type as the previous equation, but with lower degree constraints. So now this exactly is the setup for divide and conquer. We can apply the whole divide and conquer paradigm to this and solve this problem. So basically this is all that we have done. We have said we have reduced finding this P to finding U and V, which have these two. This is exactly the same problem, smaller type. It's two problems of the same size. So it's amenable to divide and conquer. So let's quickly see what's the recurrence relationship which we're going to have. So suppose TD is the running time to solve the original problem. D. So how much is the divide step? Notice the divide step itself involves, as was noticed, it involves a multiplication of degree d by 2 polynomials because I need to compute C tilde. And that's d polylog d. Conquer step is two problems of d by 2 each, so 2 times d by 2. Combine step is just order d. Therefore, we have the recurrence relation TD is less than 2 times d by 2 plus order that d times polylog d. So suppose this polylog d was log square, you will get an extra, this one become a log cube over here. That's what happens in the whole thing. Questions so far? Root? Sorry, I didn't follow. D by 2, yes. Yeah. So then you will be, so I want to split both. So if you're going to split it root d, then you are not splitting into equal parts. No, it's d and d minus square root d. The other part is d minus square root d. So I would, for this one, I would like to split it up into things rough. So there you, in principle, you could split it into root d parts of each root d each. You could do the same thing. Then the combined steps become a little more elaborate and even the divide steps becomes a little more elaborate. But you could do this. The divide and conquer doesn't always have to be dividing into two. You could divide into three parts. In fact, also number of parts which are the function of d can also be done. Root d, you could do this. You could do this. But notice the divide steps for this problem. Try doing it this one. The divide step becomes far more complicated because than the previous divide, than the divide step over here. Okay, so so is this clear what I've done over here, polynomial division? Yeah. Huh? Yeah. So yeah. Yeah, good. So what Chandra is pointing out is that I had this nice picture for merge sort. So merge sort, what was the picture? There was the big problem, split into the left half and the right half. And then the left half and the right half did not interfere at all the way till the end. So I could, once I split it up into two parts, this was the left half went this way, the right half went this way, and they combined only at the very end. Whereas what Chandra is pointing out is here, okay, we take the same thing. I have the original problem on degree d. I got the first half, which is this polynomial, ax minus ux. But I have to solve it all the way till the end, find u of x before I even start the second half. Because the second half requires knowledge of u. So merge sort is sort of a parallel algorithm. You can break it up into two parts immediately. Whereas this way I have said here, the breaking up of two parts, I cannot do it till I finish the first part, only then I know what is the input to the second part. So it's not a parallel algorithm. So this way of running division, polynomial division, doesn't give me a parallel algorithm, it gives me a very sequential algorithm. But there's no reason in divide and conquer that you must break it up in the two parts. You could use the solution of the first part to find out what is the question to the second part. And that's what's happening here. So, in fact, that's why we don't teach divide and polynomial division in this algorithm back in the first class in graduate class, because it's not as nice an algorithm as this. It's a sequential algorithm. You can't draw such a nice picture because I'll have to solve the second, I'll have to come all the way to this part before I even know what is the input to this part. So it's not a part in which it splits up into two parts very easily. You have to do this. Yeah. Okay, so that was polynomial division. Any other questions? Okay, so all of this is fine. Why did I state polynomial division in this much more complicated? Yeah, yes. What do you mean polynomial modulus? So I don't know. I don't know. All these algorithms involve an extra logarithmic factor. It will be amazing if you could shave off that. We don't know. There is even multiplication. I don't know how to shave this off. All of them have an extra. All these, I think, algebraic problems involving algebraic computations involve an extra log d factor. It would be amazing if I could solve this. We don't know how to do it. Huh? For this one, that will be in the bit complexity. In the field operations, I don't know. I don't know of any lower bound. Yeah, yes. Yes. Yeah. Yes. Yes. Mm-hmm. Yes. Mm-hmm. Yes. Yeah. No, no, no. So I don't see how multiplication does not behave very nicely with respect to reverse, no? So the low, for example, the low order parts, if you want to, the low order part of this will involve only low order parts of the entire thing. But the high order parts will involve both the low and the high. So you can't say the top part will just be a function of only the top part. The reason it's not parallel is because the low order part of this equation involves only low order parts of A, P, and B. But the high order part involves both the low order parts and high order part, and that's what's spoiling the parallelism, at least in the algorithm, the way I stated it. Okay? Question? Okay, now let's go back to our ODE. I won't say much on this, but I'll show you how this is very similar to the problem we saw so far. So once again, what do we have? We have, this is a problem I stated at the very first slide. We had this particular case. We wanted to solve this. Let's look the baby version of this, in which m equals 1. In other words, a naught x plus a1x px is 0. I want to find all solutions. But this is exactly the problem we solved just now. The basic version of it, which is not the differential equation. There's no even prime. This is exactly the baby version of what I solved. Polynomial division. So the m equals 1 case or the m equals 0 case, whichever is this. This is the simplest version of this problem is what was polynomial division. Now you could expect, do the exact same algorithm actually works for m equals large. You just write down the equation, think of p as the first half and the second half, solve it, you will get two differential equations, break down the problem into two differential equations, solve it, and you do it. That's all we did. So it was actually realizing that this problem, right, solving division in this way, instead of solving division the other way, is what actually helped us. So once we solved division the way I stated it, it said that this differential equation also is exactly the same case as this. The base case is just polynomial division, and we just extended the same technique to larger m. There is one complication, this one. For m equals 0, or the simplest case, there is only one unique solution. But once you go to a larger thing, it's not a unique solution. There's more than one solution that will solve this one. For example, even if I had the first derivative, the solution will be an affine space. So there is a possibility if you don't keep the bookkeeping, it will blow up. In divide and conquer, if it's not a unique solution, it can just blow up at each step. You need to do the bookkeeping carefully, and then it's exactly whatever I said so far. So the solution, all I wanted to say was, it seemed as if this was a very different problem, but actually once we realized division can be written this way, it was exactly the same algorithm which we use for division that happened for solving the differential equation. I had a question? I think that's more or less what, I don't know why my slides take. Yeah, and that's basically what we had. Paper, I will take questions. This one at this point, yeah. This actually gave us a d log cube d algorithm to solve this problem. And this was in turn needed for the bigger problem, which we had, which was something to do with error correcting codes. Yeah, thanks. Since most of you are undergrads or high school students, I wanted to tell you a little thing about where I work and some opportunities for students. Oh, some of you over there, but there was a question in the meanwhile. Let me take that question. Yes. Yes. So what we do is, what we realize is in affines, we use the very first fact I mentioned in the first slide. So the solution is an affine space. And we sort of realize that affine space solution is such that if you know the first, for example, if it was a differential equation of the first order, that is involved only dy by dx, then it's an affine space of dimension 1. Therefore, there was only 1 degree of freedom. So either the solution will have the constant term 0. So you can find, what you want to find is a basis for the solution. You're not going to find the entire thing. You want to find the basis. And so you find a solution in which the constant term is 0. Then so suppose it's an affine space of dimension r. What you can show is the low order r coefficients are going to determine the solution. So you start off with a solution in which the low order only x power I has a non-zero coefficient, all the rest are 0 coefficient. Once you do this, you find a particular basis element. You can do this for all the R basis elements, and that is the end of this one. Yeah. Yes. Yeah. It's not obvious. It'll take a little bit of work. Let's see if I can mention it in. So once again, what we're going to have a of x plus p of x into b of x plus p prime x into c of x is 0. We'll do the same thing. We'll put p of x to be equal to u of x plus x power d by 2 v of x. So this splits as, let's collect all the u of x, b of x plus u prime x, c of x plus x power d by 2 v of x, b of x plus x power d by 2 minus 1 v of x. Am I right over here? I messed up the thing. I think there'll be a multiplication of d by 2 over here plus x power d by 2 v prime x. Am I missing a c of x here? Is 0 mod x power d. So the low order part is certainly this, which is exactly what we had. You solve it, you get the u, and then you use that u to find out this part will be with an x power d by 2. You will get another system which looks exactly, it will just have vx and v prime x in this. You plug it in back, you'll solve that, and you keep doing it. So if it was unique, this is all the solution is. It's just that it won't be unique. And then you'll have to do a little bit of bookkeeping to keep it. If it was unique, you just solve u of x. The low order part will only be this. X, you'll have to do this d by 2 minus 1. So instead of, so I will add an x here, and you have to change what you mean by low order. Low order is no longer, have I messed it up? I messed it up. There's no, this one over here, it is product over here. Yeah. The low order will not be just d by 2, it will be d by 2 minus 1 here, but that's okay. Everything works out on this. Okay. Any other question? Yes. Sorry, I didn't catch you. Yes. You could do that. You could do. It's just that if you stare at this carefully, you know that if you fix the lower order, if the affine spaces of dimension R, if you fix the lower order R terms of the polynomial, there exists only one extension. Therefore, you can know which thing you are going along. You fix U in a particular fashion, and once you fix that, there's only one extension to go a bit. This needs a little bit of thought. It requires some more notation. I don't want to skip it. You can look at the actual paper which we have, which has all the details of the result. Any other question? Yes. Yeah. Uh, you could, for what do you have, for differential equations, I think it was polynomial in D. Possibly you could use a little more structure for these polynomials to say it was quadratic, but that was the best prior to our work. Yeah. Any other questions? Yeah. I just wanted to say, start with a few words on our school and what opportunities. So I come from TIFR and I belong to the School of Technology and Computer Science, which is one of the 3 schools in TIFR. So for those of you who don't know, TIFR is located in Bombay. It's in fact, it's in a very nice part of Bombay. It's the southern tip of Bombay. TIFR is one of the research institutes in the country devoted for the fundamental sciences. So computer science is one of the sciences I was studied there, but we also do mathematics, natural sciences, which includes physics, chemistry, and biology. It's one of the premier research institutes in the country for this. Just a few words. So School of Computer Science is actually a very old school, though it was founded very recently. In fact, it is where India's first computer was actually built. The TIFR, which was not too long after the ENIAC, which is the world's first computer. That happened in the early 50s. Very soon after TIFR built the first computer, and several other systems in the country were actually deployed in TIFR before TIFR became, the computer science department became one which worked actively in various aspects of theoretical computer science. Currently we have strengths in these very aspects of computer science. We do a lot of interdisciplinary research in the theoretical aspects of computer science, learning, information, and decision science. We're about 17 faculty, and we have a very nice graduate program going on with about 29 students. Just wanted to say a few things about our students. Our students have been doing incredible work over the last few years. They've been sort of consistently winning the best awards in various venues, both research paper venues and best thesis awards. And that's our graduate program. Our TIFR is not just based in Bombay, it's a multi-center campus. We have 7 campuses across the country. There's TIFR, there's ICTS Bangalore, NCBS Bangalore, which is for the biological sciences, Pune for astrophysics, HBCSE for science education, TIFR Hyderabad, which does mostly physics and chemistry, and TIFR Center for Applied Mathematics in Bangalore. Places for more, these are for more, so far as I've been talking only about graduate, this one. We also run several summer programs for this one. One summer program which is tailored to women is in fact to promote science, research as a career option among women. We run a sort of a 2-week program every year called the Vigyan Vidushi program. Those of you who are interested, this year's program is going to be from the 16th of June to the 27th of June, and it will be in the TIFR Mumbai campus. This is all pictures are from our campus picture. So even if you're not coming to study, I think visiting TIFR campus is a worthwhile effort. Those of you who are interested for it, please do apply by 16th March. In addition to these, actually we have a veritable collection of courses, several of our courses in various topics taught, and most of our courses we actually put them up online. So if you go to our school's YouTube channel, several of the courses are publicly available, and these are fairly interesting courses. It's a very rich source of this one. I had anything else? Yeah, that's all. Thank you.